Alright, today we are going to be talking about parent trig graphs in a window pane. And we're going to be using a graphic organizer, which you should have picked up, to help you understand the characteristics of the parent trig functions. So make sure, before we begin, that you have your parent trig window pane graphing worksheet that we gave you. And make sure that you also have your unit circle worksheet that we did in class. Let's talk a minute about periodic functions. What does it mean for a function to be periodic? It means that something that has a cycle or repeats itself. So can you think of some other periodic functions that occur in daily life? One might be, what is the period for time on a clock? Think about how the clocks work, and that would be 12 hours. What's the period for the days of the week? And that would be 7 days. What is the period for the cycle of months? Well, again, that would be 12 months in a year. Trig functions will have similar behavior repeating after a certain period of time. So let's go back and talk about the unit circle a little bit that you formed. Your unit circle is centered at the origin, and you should have learned what the radius of your unit circle is. And that would be 1. The radius of the unit circle is 1. Which part of your coordinates represents the sine of an angle? And that would be the y value. Which part of your coordinates represents the cosine of an angle? And that would be the x of the coordinates. And I want you to write these on the back of your unit circle. So sine of an angle theta in the unit circle is the y value. Cosine of theta is the x value in the coordinate pair. Tangent is going to be the y over the x. Cosecant, which is one of the reciprocal trig functions. Cosecant is the reciprocal of sine, which means since sine of an angle is y value, then cosecant of that same angle is 1 over the y. Same with secant. Secant is the reciprocal of the cosine function. So cosine of theta is x, and secant of theta is 1 over x. And same with tangent. Tangent and cotangent are reciprocals of one another. And you can see the y over the x for the tangent and the x over the y for the cotangent. So again, pause this and write these on the back of your unit circle. Alright, so let's talk a minute about that worksheet that you've completed and look at the column with cosine theta and tell me what the highest value in the column is. And you should see that the highest value of the column for cosine theta is 1. What's the lowest value in that column? Again, you should see -1. So now in your window pane, you should have some things I'd like you to label. I'd like you to label the top side of the left-hand side here as 1 and the bottom side as -1, and of course right here is considered to be 0. I want you to halfway through this window pane, I want you to give me a pi halves, which hopefully you will recall is the same as 90 degrees. And pi would be halfway through the whole entire window pane, which represents 180 degrees. But again, we're getting used to radians now. And all the way across would be 2 pi. So that means if I have 1 pi right here and 2 pi right here, then 1½ pi or 3/2 pi would belong halfway between them. Right? Now we're going to plot some points. We're going to use our unit circle. So you're going to look and see that if the angle is 0 and we're looking for cosine, we're looking for the x coordinate on your unit circle at 0. So again, that would be 1. And then I want you to look at pi halves, and I want you to find out what the coordinate pair is at pi halves. And the x value there should be 0. Same thing over at pi. The coordinate pair there should be -1, 0. So that means that the x value there at pi would be -1. Come around to 3 pi halves, or 270 degrees, and you see that the x coordinate is 0 again. And then at 2 pi, you should have come fully around that circle, that unit circle, and be back where you started, again at 1. Just so that we get a visual of how to connect these dots, I'd like to put some things in between it. So I'm going to put a pi force, and if you look at pi force, the x value there is a √2/2, which is the same thing as about 0.7. I just wanted you to realize that it's not a linear relationship between this and this. Okay, it's a curved sort of relationship there. And at 3 pi force, you again have another negative √2/2, or -0.7. Now if you kind of connect these, you see my silly attempt at trying, but you see that it looks curved, like a sine or cosine graph looks. And if you just continue that across there, you see an entire window pane that includes one period of the cosine graph. Because here we see we had the highest point of 1, and we traveled along here until the lowest point, -1, and then returned to the beginning point to start again. So let's talk a minute about amplitude. When you're talking about amplitude, that's why this window pane is really effective, because the top part of the box is the highest place that these cosine and sine graphs are going to go, and the bottom's the lowest. And so if we have it directly in half here, this is sort of the center of the graph along here. It goes as high as 1 unit above that middle region, or 1 unit below, and so the amplitude of this graph should be 1. And what about period? Period is supposed to be the amount of time for you to get from a hill to the hill again, or a valley to another valley again, depending how you start the graph. So in this case, we went from the right-hand side of the top of the hill until the left-hand side to return again to the same spot. So the total period of this would be 0 to 2 pi, meaning the period would be 2 pi. Alright, so what is our y-intercept of y equals cosine of x? That would be y equals 1. Where do the x-intercepts occur? Let's talk back a little bit. The x-intercepts are going to occur on my little window pane of pi halves, and then again at 3 pi halves. So if you'll note, in this window pane, the first place we get 1 is at pi halves, but then after that, they're going to occur in both directions for every pi, for every 180 degrees there. So we went from 90 to 170. Okay, so there's a difference of pi radians, or 180 degrees there. So again, the x-intercepts are going to occur every pi beginning at pi halves. What appears to be the domain of cosine x? So the domain, again, from this appears to be 0 to 2 pi. But what do we know about periodic functions? We know that they continue in both directions forever and ever, so it appears that the domain would be all real numbers. What about the range? D says, what's the range of the function? Well, the range definitely shows on this window pane as being between -1, again including -1, until +1, inclusive as well. At what value or values of x does the function reach a maximum? So let's go back there. And then f will be, where do we reach our minimum? So our maximum values we found are 1. So those in our window pane are occurring at 0 and then again at 2 pi for our maximum. So it would appear that they are going to occur every 2 pi from 0 in both directions, every 2 pi. At what value or values of x do we reach a minimum? Well, right here we have it at pi, and then when would that happen again outside the window? We would get back there at 3 pi and at 5 pi. So again, every 2 pi we're going to reach our minimum. Okay, and G. Would y equals cosine of x be considered even or odd or neither? And explain. Okay, if you'll recall, for a function to be even, it must have symmetry over the y-axis. If it's going to be odd, it must have symmetry over the origin. So if we think about extending this, because right here is our y-axis, it appears to me that we would have symmetry over the y-axis there, because this would continue to have its hill and its valley and be reflection across the y-axis. So I would say that y equals cosine is considered to be even because of that symmetry across the y-axis. Alright, so let's do the same thing with sine that we did with cosine just a moment ago. And remember that in our unit circle, sine of the angles is the y value. So let's place our next window pane and label the values that we did earlier, where we had -1 as the lowest point, because it is the lowest value in your column on your worksheet. That was sine of theta. And then halfway between -1 and 1 would be our 0. So make sure you place that on here. Good. And then pi halves and pi and 3 pi halves and 2 pi along there. Now we're going to use our unit circle again to plot points. So if the angle is 0 and I'm looking at my unit circle, I should see that the y value is 0 there. At pi halves, I should see that the y value is 1. At pi on my unit circle, I should see that the y value is back to 0. At 3 pi halves, I should see that the y value is -1. And at 2 pi, we come back to 0. So if we can assume that it functions just like the cosine function did, and we don't need to plot other points, we would still have the same kind of sinusoidal graph. That's the name for these cosine and sine graphs that have the hills and valleys in them. Alright, so we again have one period graphed here. So what's the y-intercept of sine? Well, that would be 0. So again, this is our y-axis over here. Where do the x-intercepts occur? Well, we have them at 0, and then at pi, and then at 2 pi. So it appears to me that every pi, beginning at 0, and I use beginning kind of loosely, because you could begin it anywhere. I just usually try to get as close to 0 for my beginning value as possible. And then we're having an x-intercept every pi. What appears to be the domain? Again, the domain of sine of x appears to be the same thing it was for cosine. Periodic and continuing off in both directions to be all real numbers. And the range, again similar. The highest value we reach is 1. The lowest value we reach is -1. So our range would be between -1 and 1. Inclusive. At what value do we reach a maximum and a minimum? Our maximum, the first one again, that's relative in here, but the first one in our window is pi halves where we reach a maximum. And the next time we would is outside this window. 2 pi more than this would be our next maximum. So Our minimum looks like occurs at 3 pi halves here and would occur every 2 pi as well. Would occur again outside this window. And would be considered even, odd, or neither. Well, if we consider the path of this coming over this direction and the symmetry contained there, I would say that it's an odd function, meaning that it has symmetry across the origin. Alright, so let's talk about a little thing to help you remember. This little snow cone visual. So remember how sine had an actual hill, full hill, and a valley, and began at 0, right? And then our cosine function started at 1 and ended at 1. Do you remember that? So if you can visualize the snow cone for a minute, the sine of 0 is 0. So we have the sine of 0 is 0. So you can remember it starts there at 0 and climbs from there, like the snow cone does. Then, if you think about the cosine of 0, the cosine of 0 is 1, and you can kind of visualize it here and realize that you start on the upper end of the cosine and return to the hill there. The sine graph is going to start off as the snowball shape, and the cosine is going to start off in the cone shape. And hopefully that can help you remember how they behave. Alright, so for your assignment to bring to class, next class period, you're going to consider these two functions. And they should look a little bit familiar in that we've talked about A, B, C, and D in relation to our transformations unit. So now we can use A and B and C and D in relation to these two parent graphs and see what they do. So I want you to consider those equations, and I want you to describe how A and B and C and D would affect the parent graphs for sine and cosine. And we're going to collect your responses at the beginning of next class. All right, we will see you soon.